the RMS speed of the oxygen molecule at this temperature. You have two things to calculate. Let's pick our data. The volume of the gas is 1 liter, and convert that to meter cube. That will be 10 to the power of -3 meter cube. Is that right? 1 liter is 1,000th of a meter cube. The temperature is 0 degrees Celsius, 273 Kelvin. Pressure is 1 atmosphere. We are using all absolute units. Volume in meter cube, pressure in Pascal. 1 atmosphere is 1.01 times 10 to the 5 Pascal. The total translational kinetic energy of n moles of a gas. Do you remember that equation we just got 2 slides ago? The total translational kinetic energy of n moles of a gas is 3/2 nRT. Is that right? Yes. So this is the total translational kinetic energy, which is 3/2 nRT. If you remember, we had it earlier as 3/2 uppercase NKT, which is the same as 3/2 nRT. Well, we need to find the value of this. Is there any way we can do this? Do we know N, the number of moles? Well, of course we know R. When volume is measured in meter cube and the pressure in Pascal, the value of N is 8.314 joules per mole per Kelvin. Well, because we don't know N, we are going to take another route. You know, NR or nRT. What is the universal gas law? PV equal to nRT. Is that right? So you can see I colored nRT red because I can replace that nRT now by PV. Why? I know the pressure, I know the volume, therefore this is a much easier route for us to take. The total translational kinetic energy of the n moles of gas is 3/2 PV. Now, put in the values of P. P is 1 atmosphere, 1.01 times 10 to the 5 Pascal. And the volume is 10 to the -3 meter cube. That gives you K as 151.5 joules. You see, in order to get K in joules, you need to have the volume in meter cube and the pressure in Pascal. So you need to use the absolute unit. Alright, we now need to find the RMS speed of oxygen molecule. Now what's the equation for RMS speed of a molecule? V RMS is square root of 3RT over the molar mass. That means you need the molar mass. What is the molar mass of oxygen? The molar mass of oxygen is 32 grams. The molecular weight of oxygen is 32. The atomic weight is 16. But oxygen is a diatomic gas. That means its molecule is made up of 2 atoms. So the molecular weight of oxygen is 32. That means the mass of 1 mole of oxygen is 32 grams, which is 0.032 kilogram. V RMS is square root of 3RT over the molar mass. We know the value of R, we know the value of T, and now you know the value of M. Therefore, using all those values, we get V RMS is 461.3 meter per second. At 0 degrees Celsius, the oxygen molecules have an average speed of 461.3 meter per second. It's an enormous speed. Alright, let's do another problem. In a period of 1 second, 5 times 10 to the 23 nitrogen molecules strike the wall with an area of 8 centimeters squared. If the average velocity of the molecules is 300 meters per second and strike the wall head-on in a perfectly elastic collision, what is the pressure exerted on the wall? The mass of nitrogen molecules is 4.68 times 10 to the negative 28 kilogram. Alright, let's pick the values that are given. And the total number of molecules are given to us, 5 times 10 to the 23. The average velocity of a molecule is given to us, is 300 meters per second. The mass of a molecule is given to us, that is 4.68 times 10 to the negative 28 kilogram. The area on which these molecules collide is A equal to 8 times 10 to the negative 4 meters squared. What do we need to find? We need to find the pressure exerted on the wall. Well, first we find the total force. The change in momentum of one molecule due to collision. You remember we said we obtained that as 2mvx. mvx is the momentum forward. It collides and rebounds with a momentum negative mvx. Therefore, the change in momentum is mvx minus negative mvx is 2mvx. That will be 2 times mass of one molecule multiplied by the speed, the average speed of that molecule. That is 2.81 times 10 to the negative 25 Newton second is the change in momentum of one molecule. And how many molecules are there? Well, there are these many molecules. Therefore, the change in momentum of these many molecules, 5 times 10 to the 23 molecules, is multiply the change in momentum of one molecule with the total number of molecules, and that will give you delta P. The total change in momentum is 0.1404 Newton second. Alright, the rate of change of momentum is, this change in momentum occurred during a time 1 second. So the rate of change of momentum is delta P divided by delta T. Delta P is this, and delta T is 1 second. Therefore, the rate of change of momentum is 0.1404 Newton. And what does rate of change of momentum represent? The rate of change of momentum is a measure of the force. So, this is a measure of the force F acting on the wall due to the collision, because the change in momentum is due to the collision. So that change in momentum is a measure of the force exerted by the molecules on the wall. So what is the force exerted on the wall? This is the force exerted on the wall. Pressure is force per unit area. So divide this force by the area of the wall. That will be 0.1404 Newton divided by 8 times 10 to the negative 4 meters squared. That gives you 175.5 Newton per meter squared is the pressure exerted on the wall. And you know Newton per meter squared is a Pascal. Okay, now these problems are representative problems and you must be familiar in doing this. Let's do another problem. At what temperature will the RMS speed of a hydrogen molecule equal to 331 meters per second? Well, the information you have, hydrogen. Now, what is the molar mass of hydrogen? You have any idea? Well, if you look at the periodic table, it will give you that value. The RMS speed is given to us is 331 meter per second. We need to find the temperature. Vrms is square root of 3RT over M. And what is therefore temperature? The temperature solved for T, square both sides. Vrms squared equal to 3RT over M. Therefore, T equal to Vrms squared times M divided by 3R. You know the value of R. Do you know the value of M, the molar mass of hydrogen? The molecular weight of hydrogen is 2. That means the molar mass is 2 grams per mole, which is 0.002 kilogram per mole. So, using the values of Vrms, the molar mass of hydrogen, and the value of R, we can now calculate the temperature. The temperature is 331 squared times 0.002 all over 3 times H.314, and that is H.79 Kelvin. You can see we have a large amount of information about the gases. Now you can calculate. Now you remember that the theoretical formulations we did in this class is based on assumptions, and we will be now testing these assumptions as we go on. Now, if the results that we obtained, that, for example, this is the results that we obtained from our assumptions about the behavior of gas molecules. Now, when you test it, if you can measure the actual speed of molecules, and if the equation can stand that test, then our assumptions are right. But sometimes we may have to go back and revisit our assumptions and make changes to it. We will see as we go on. Alright, I'm going to stop this lesson here. I will get back to you with another lesson on thermodynamics a little later.